The closest star to our Sun is harboring worlds that shouldn't exist, Alpha Centauri, close enough to reach in a human lifetime with the right technology. And what scientists are discovering on the planets circling those stars is forcing them to confront a terrifying possibility. We might not be alone, and our neighbors might be living in hell. If you're curious about these mysteries, make sure to give this video a like. It takes just 1 second, but your support makes all the difference to keep this channel going. Now let's begin. Let me paint you a picture. Imagine standing in the southern hemisphere on a clear night. You look up and there it is, Alpha Centauri, shining brightly in the constellation Centaurus. To your naked eye, it appears as a single brilliant star, the third brightest in the entire night sky. But here's where things get interesting. That single point of light? It's actually 3 stars locked in an intricate cosmic dance that's been going on for billions of years. The first member of this stellar family is Alpha Centauri A, a star remarkably similar to our own Sun. It's what astronomers call a solar twin, a G-type main sequence star that's only slightly more massive and slightly brighter than the star that gives us life. Then there's Alpha Centauri B, a K-type star, a bit smaller and cooler than its companion. These 2 stars orbit each other in an elliptical waltz, coming as close as 11 times the Earth-Sun distance at their nearest approach, and swinging out to nearly 36 times that distance at their farthest point. One complete orbit takes about 80 years. But wait, there's a third member of this family, far from the central pair, separated by a distance of about 13,000 times the Earth-Sun distance. There's a small red dwarf star. We call it Proxima Centauri, and it's technically the closest individual star to our Sun. Proxima is tiny compared to its siblings, dim and cool, barely visible even through a telescope. But don't let its modest appearance fool you. Proxima has been at the center of some of the most exciting discoveries in modern astronomy. Here's what makes this entire system terrifying, and I mean that in the most awe-inspiring way possible. We're talking about a cosmic neighborhood that's so close, yet so utterly different from our own solar system. Alpha Centauri A and B are locked in a gravitational embrace that makes planet formation incredibly complex. The zones where planets can exist are constantly being tugged and pulled by competing stellar forces. Any world trying to form there would have had to survive a chaotic birth, navigating gravitational interference that could easily have flung it into the void of interstellar space. And then there's Proxima Centauri. This little star is violent. It's an active M dwarf that regularly unleashes powerful stellar flares, bursts of radiation, and charged particles that would make our Sun's solar flares look like gentle breezes. Imagine a planet orbiting that close to such a temperamental star. One moment it's bathed in dim red light, the next it's being hammered by radiation levels that could strip away its atmosphere, molecule by molecule, year after year. But here's the beautiful paradox. Despite all this chaos, despite the gravitational tug-of-war and the stellar violence, planets exist there. Real worlds orbiting real stars, just 4.3 light-years from where you're sitting right now. The question isn't whether planets exist at Alpha Centauri anymore. The question is, what are they like? What strange conditions might exist on their surfaces, and could any of them harbor life? Let's start with what we know for certain. Around Proxima Centauri, astronomers have confirmed the existence of at least 3 planets. The most famous is Proxima Centauri B, discovered in 2016 using the radial velocity method. This technique measures the tiny wobble in a star's motion caused by the gravitational tug of an orbiting planet. Proxima b is fascinating because it orbits within what we call the habitable zone, that sweet spot where temperatures might allow liquid water to exist on a planet's surface. Proxima b completes one orbit around its star every 11.2 days. Think about that for a moment. A year on Proxima b is shorter than 2 weeks on Earth. It's located just 7.5 million kilometers from its star, about 5% of the distance between Earth and our Sun. But remember, Proxima Centauri is much dimmer and cooler than the Sun, so despite being so close, Proxima b receives a similar amount of stellar energy as Earth does. At least that's the simplified version. The reality is far more complex and, frankly, more terrifying. Proxima b might sit in the habitable zone, but that doesn't mean it's habitable. Let me explain why. Proxima Centauri is what astronomers call a flare star. In 2018, astronomers observed a superflare from Proxima that increased the star's brightness by a factor of nearly 70 over just a few seconds. The radiation from that single event was intense enough that if Proxima b has an atmosphere, it would have been blasted with extreme ultraviolet and X-ray radiation. Now imagine you're standing on the surface of Proxima b during one of these flare events. The sky, normally bathed in dim reddish light, suddenly blazes with intense radiation. If you were unprotected, you'd be exposed to radiation levels thousands of times higher than anything we experience on Earth, even during our Sun's most active periods. Any life that exists there would need incredible adaptations to survive, perhaps deep oceans to shield organisms from the radiation, maybe thick atmospheres with powerful magnetic fields to deflect the worst of the stellar wind. Or life could exist underground in caves and crevices, venturing to the surface only during quiet periods. But Proxima b isn't alone. There's Proxima d, a smaller world discovered more recently, orbiting even closer to the star with a period of just 5.1 days. This planet is likely too hot for life as we know it, baked by its proximity to Proxima despite the star's relative dimness. And then there's Proxima c, a more massive planet, possibly a super-Earth or mini-Neptune, orbiting much farther out with a period of about 5.2 years. This world is likely frozen too far from the star's warmth to maintain liquid water on its surface. Each of these worlds tells us something profound about planet formation in such a challenging environment. They survived the chaotic early days of their system when Proxima was young and even more violent than it is today. They've endured billions of years of stellar bombardment, and they're still there, silently orbiting their temperamental star. But here's where the story takes an even more incredible turn. In August of 2025, NASA announced that the James Webb Space Telescope had found strong evidence of a giant planet orbiting Alpha Centauri A itself. Not Proxima, but the Sun-like star at the heart of the binary system. This discovery, if confirmed, would be extraordinary for several reasons. First, this candidate planet, let's call it Alpha Centauri A planet, or just planet S1 for now, would be orbiting at about 2 astronomical units from its star. That's roughly twice the distance between Earth and our Sun, placing it in a region similar to where Mars orbits in our solar system. But unlike Mars, this world appears to be a gas giant, roughly the mass of Saturn. Imagine a massive planet with stunning rings, orbiting a star that looks almost exactly like our Sun, just over 4 light-years away. The detection itself is a technological marvel. The James Webb Space Telescope used its mid-infrared instrument called MIRI to observe Alpha Centauri A at a wavelength of 15.5 micrometers. At these wavelengths, the telescope can detect the heat signature of planets, seeing them not by reflected starlight, but by their own thermal glow. The challenge is immense because even though Alpha Centauri A is relatively close, the contrast between the star and the planet is still about 55,000 to 1. It's like trying to spot a firefly next to a lighthouse from hundreds of kilometers away. What makes this discovery even more remarkable is the method used to confirm it. Because Alpha Centauri A and B orbit each other, astronomers had to account for the motion and light of both stars. They used a technique called reference star differential imaging, essentially using Alpha Centauri B as a reference point to subtract its contribution and isolate the signal from around Alpha Centauri A. This is the first time this technique has been successfully applied with the James Webb Space Telescope, opening new possibilities for detecting planets in binary star systems. Speaking of finding worlds in other star systems, if you're fascinated by the challenge of actually reaching these distant planets, you might want to check out my other video on how long until humans achieve interstellar travel. It explores the technologies we'd need to develop to journey to places like Alpha Centauri and the incredible obstacles we'd have to overcome. I'll leave the link in the description and on the card above. Now let's talk about what this potential gas giant means for the Alpha Centauri system. If this planet exists, it has profound implications for the possibility of other worlds in the system. Gas giants act as cosmic shepherds in planetary systems. Their gravity can scatter smaller bodies, protecting inner rocky planets from constant bombardment by comets and asteroids, similar to how Jupiter protects Earth. But they can also destabilize orbits, making it difficult for smaller planets to form in certain regions. The presence of a Saturn-mass planet at 2 astronomical units from Alpha Centauri A tells us that planet formation occurred successfully in this binary system despite the gravitational interference from Alpha Centauri B, and if planets formed there, they might have formed closer to the star as well, in the habitable zone where liquid water could exist. We're talking about the real possibility of an Earth-like world orbiting a Sun-like star, right next door to us in cosmic terms. But here's what keeps astronomers on the edge of their seats. The observations from Webb also searched for something else, exozodiacal dust. This is dust similar to the zodiacal light we see in our own solar system, faint bands of light caused by sunlight reflecting off dust particles left over from the formation of planets. The sensitivity of these observations was extraordinary. They reached levels capable of detecting dust clouds just 5 to 8 times brighter than our own zodiacal cloud. And you know what they found? Almost nothing. The dust levels around Alpha Centauri A are incredibly low, possibly even lower than in our solar system. This might sound boring, but it's actually thrilling news. Low dust levels mean better conditions for future observations. When we eventually build telescopes powerful enough to directly image Earth-sized planets around nearby stars, dust is one of the major obstacles. It scatters light, creates noise in the data, and makes it harder to distinguish the faint signal of a rocky planet from the background. The fact that Alpha Centauri A appears to have such a clean environment means that when the time comes, we'll have a better chance of seeing what's really there. And the observations aren't stopping there. Astronomers are planning follow-up observations with Webb to confirm the existence of this giant planet candidate. They need to watch it over multiple epochs, tracking its motion to verify that it's truly orbiting Alpha Centauri A and not just a background object or an artifact in the data. If the planet is real, they'll be able to determine its exact orbit, its mass, and eventually even some details about its atmosphere. Think about what that means. We could study the atmospheric composition of a planet orbiting our nearest stellar neighbor. We could look for methane, water vapor, ammonia, all the chemical signatures that tell us about how that world formed and what conditions are like there. We could compare it directly to Saturn, Jupiter, and the ice giants in our own solar system to understand how planet formation varies from one star system to another. But let's zoom out for a moment and consider the bigger picture. The Alpha Centauri system isn't just a collection of stars and planets. It's a laboratory for understanding how planetary systems form and evolve in challenging environments. Binary star systems are incredibly common in our galaxy. Some estimates suggest that more than half of all stars exist in binary or multiple star systems. Yet most of the exoplanets we've discovered so far orbit single stars like our Sun. Why? Because planets in binary systems are harder to detect and their formation is more complex. The gravitational dance between two stars creates zones of stability and instability. There are regions close to one star where planets can form and maintain stable orbits unaffected by the distant companion. These are called S-type or satellite orbits. Then there are regions far from both stars where planets can orbit the binary pair as if they were a single object. These are P-type or circumbinary orbits, but in between there's chaos. Orbits become unpredictable, resonances amplify small perturbations, and planets either get ejected from the system or crash into one of the stars. If you're enjoying this deep dive into our cosmic backyard, make sure to hit that subscribe button and give this video a thumbs up. Your support helps me bring you more content about the wonders of the universe. Alpha Centauri A and B are separated by distances that place them right in this complex middle ground. The binary orbit takes about 80 years, and during that time, the distance between the stars varies dramatically. When they're closest, at what astronomers call periastron, they're only about 11 astronomical units apart. When they're farthest at apastron, they're separated by nearly 36 astronomical units. For comparison, that's like having a second sun that swings from just beyond Saturn's orbit to beyond Neptune's orbit in our solar system. Any planet trying to maintain a stable orbit around Alpha Centauri A has to contend with this periodic gravitational tug. From Alpha Centauri B computer simulations have shown that stable orbits are possible, but they're limited. Rocky planets could potentially exist in stable orbits out to about 3 astronomical units from Alpha Centauri A. Beyond that, the influence of Alpha Centauri B becomes too strong, and orbits become chaotic over millions of years. This is why the potential discovery of a gas giant at 2 astronomical units is so significant. It's right at the edge of the stable zone, a cosmic tightrope walker that's been maintaining its balance for billions of years. If it exists, and if it's been there since the system formed roughly 6 billion years ago, it tells us that planet formation can succeed even in these dynamically complex environments. Now let's talk about Proxima Centauri's relationship to the binary pair. For a long time, astronomers weren't even sure if Proxima was gravitationally bound to Alpha Centauri A and B, or if it was just passing by in space. The distances involved are enormous. Proxima orbits the central binary at a distance of about 13,000 astronomical units, or roughly 0.2 light-years. At that distance, the gravitational bond is tenuous, easily disrupted by passing stars or giant molecular clouds. Recent studies using precise measurements from the Gaia Space Telescope have confirmed that Proxima is indeed bound to the system, but its orbit is incredibly long, possibly taking hundreds of thousands to millions of years to complete. This means that over the lifetime of the system, Proxima's distance from the central binary has varied. Sometimes it's been closer, sometimes farther. These changes in distance could have had profound effects on any planets in the system, stirring up comets from distant reservoirs and potentially triggering impact events on inner worlds. Here's where things get even more fascinating. Recent observations published in early 2025 using an instrument called NIRPS, the Near Infrared Planet Searcher, achieved something remarkable. They broke the 1 meter per second precision barrier in detecting the wobble of Proxima Centauri caused by its orbiting planets. This level of precision is extraordinary. We're talking about measuring velocities smaller than human walking speed on a star that's 4.2 light-years away. Why does this matter? Because with this level of precision, astronomers can detect smaller and smaller planets. They can refine the masses of known planets like Proxima b, Proxima c, and Proxima d, and they can search for additional worlds that might be hiding in the data. There's growing evidence that the Proxima system might host even more planets, perhaps smaller rocky worlds, or additional ice giants in the outer regions of the system. Every new planet we discover around Proxima tells us more about the diversity of planetary systems. It challenges our assumptions about where planets can form and what conditions allow them to survive. And it forces us to confront an uncomfortable but thrilling reality. The universe is far stranger and more complex than we ever imagined. Let me share something that gives me chills every time I think about it. The light you see from Alpha Centauri when you look up at the night sky left that system just over 4 years ago. In cosmic terms, that's nothing. A single heartbeat. When you look at Alpha Centauri, you're seeing it almost as it is right now. The planets orbiting those stars, if they exist, are out there right now, moving through their orbits, experiencing whatever strange weather patterns or geological processes occur on their surfaces. If there's life on Proxima b, and that's still a massive if, those organisms are living their lives right now perhaps completely unaware that just over 4 light-years away there's another star with its own planets, one of which is home to billions of creatures asking the same questions they might be asking. Are we alone? What else is out there? This connection to the present tense is something we don't have with most astronomical objects. When you look at a distant galaxy billions of light-years away, you're seeing ancient history, light that left when the universe was young. But Alpha Centauri, that's our neighborhood. That's happening now in real time, just over the cosmic street from us. The technological achievement required to study Alpha Centauri is staggering. Let's take a moment to appreciate what astronomers have accomplished. The James Webb Space Telescope, orbiting nearly 1.5 million kilometers from Earth at a gravitationally stable point called L2, is cooled to temperatures just above absolute zero. Its 18 gold-coated beryllium mirrors work together as a single 6.5-meter aperture, collecting infrared light from the cosmos. And with this instrument, scientists pushed the boundaries of what's possible, detecting a faint point of light next to one of the brightest stars in the southern sky. The observations required meticulous planning. Alpha Centauri A is so bright that even with coronagraphs, masks that block out the star's direct light, the scattered light creates enormous challenges. The team had to observe the system at multiple epochs, watching how the positions of the stars changed relative to background objects. They had to account for the orbital motion of Alpha Centauri A and B around each other. They had to filter out noise from cosmic rays, detector artifacts, and the faint glow of zodiacal dust in our own solar system that sits between us and Alpha Centauri. And after all that work, after processing terabytes of data through sophisticated algorithms, a faint signal emerged, a point source designated S1, appearing at a separation of about 1.5 arcseconds from Alpha Centauri A, corresponding to a physical distance of roughly 2 astronomical units. The signal-to-noise ratio was between 4 and 6, strong enough to be compelling, but not yet definitive. That's why confirmation observations are crucial. Science demands rigor, especially when the stakes are this high. Now, imagine for a moment that this planet is confirmed. Imagine that we definitively prove there's a Saturn-like world orbiting Alpha Centauri A. What comes next? The scientific community would immediately start planning more detailed observations. We'd want to know everything about this planet. Does it have rings like Saturn? Does it have moons? What's its atmospheric composition? Is it actively forming moons right now through processes similar to those that created Saturn's magnificent satellite system? These questions might seem academic, but they have profound implications for understanding planetary systems as a whole. Saturn's moons include worlds like Enceladus and Titan, both of which are considered potential habitats for life. Enceladus has a subsurface ocean that erupts through geysers at its south pole, spewing water and organic molecules into space. Titan has lakes and rivers of liquid methane on its surface, and possibly a water ocean beneath its icy crust. If Alpha Centauri A has a similar gas giant, could it host similar moons? Could there be habitable environments hiding in orbit around a giant planet, rather than on a rocky world orbiting the star directly? This is the kind of thinking that gets astrobiologists excited. We're learning that life doesn't need Earth-like conditions to thrive. It needs liquid water, organic molecules, and energy sources. Those conditions can exist in many different environments, from the surfaces of rocky planets in habitable zones to subsurface oceans on icy moons, to potentially even the upper atmospheres of gas giants where complex chemistry occurs. Let's shift our focus back to Proxima Centauri for a moment, because there's another piece of this puzzle that's deeply unsettling. Recent observations using the XMM Newton X-ray Space Telescope, published in February of 2026, provided time-resolved X-ray spectra of Proxima. These observations revealed just how violent the radiation environment around this star really is. During flare events, the X-ray luminosity of Proxima can increase by factors of hundreds or even thousands compared to its quiet state. For Proxima b, orbiting so close to this active star, this means constant bombardment. Even during quiet periods, the planet receives X-ray and extreme ultraviolet radiation at levels roughly 400 times higher than Earth receives from the Sun. During flares, that number skyrockets. The implications for atmospheric retention are severe. Unless Proxima b has an exceptionally strong magnetic field and a thick atmosphere to begin with, it's likely losing atmospheric mass at a significant rate. Computer models suggest that over the lifetime of the Proxima system, a planet like Proxima b could have lost the equivalent of an Earth ocean's worth of water or more through atmospheric escape driven by this intense radiation. If the planet started with a thick, water-rich atmosphere, it might have enough reserves to maintain habitable conditions despite the losses. But if it started with a thinner atmosphere, it could be a desiccated, radiation-scorched world by now, more like Mars than Earth. Yet here's the paradox that makes this all so fascinating. Despite these harsh conditions, we can't rule out the possibility of life on Proxima b. Life on Earth exists in environments we once thought impossible. Deep-sea hydrothermal vents, subglacial lakes in Antarctica, rocks kilometers beneath the surface, even inside nuclear reactors. Life adapts. Life finds a way. If organisms on Proxima b evolved under high radiation conditions from the beginning, they might have developed incredible DNA repair mechanisms, radiation-resistant biochemistry, or behaviors that allow them to shelter during the worst flare events. There's also the possibility of a thick atmosphere providing shielding. If Proxima b has an atmosphere tens or even hundreds of times thicker than Earth's, the surface radiation levels might be tolerable. The planet could be tidally locked, always showing the same face to its star, with one hemisphere in permanent day and the other in permanent night. But atmospheric circulation could distribute heat around the planet, creating a twilight zone along the terminator, the boundary between day and night, where conditions might be surprisingly Earth-like. Recent advances in our understanding of tidally locked planets have overturned earlier assumptions. We used to think such planets would have extreme temperature gradients that would freeze out the atmosphere on the night side. But sophisticated climate models show that with enough atmospheric mass and the right composition, heat transport can maintain relatively stable temperatures across the planet. There could even be liquid water on the night side, fed by precipitation from water vapor transported from the day side. Think about what a world like that would look like. Standing on the surface in the twilight zone, you'd see Proxima Centauri hanging motionless in the sky, a giant red orb providing dim crimson light. The sky might have strange colors shifted toward the red and infrared, with atmospheric scattering effects completely different from Earth's blue sky. If you traveled toward the day side, the landscape would grow brighter and hotter until eventually it became uninhabitable. Journey toward the night side and you'd encounter eternal darkness, possibly frozen landscapes, or perhaps dark oceans warmed from below by geothermal heat. This is science fiction becoming science fact. These aren't just imaginative speculations. These are scenarios that astronomers are actively modeling using real physics, real data from planetary observations, and real measurements of Proxima Centauri's properties. The challenge now is to actually observe these planets in detail. The radial velocity method that detected Proxima b tells us the planet exists and gives us information about its mass and orbit, but it doesn't tell us what the planet looks like. It doesn't reveal whether it has an atmosphere, what that atmosphere is made of, or whether there are continents and oceans on its surface. For that, we need direct imaging or transit spectroscopy, and both are incredibly difficult with current technology. Direct imaging of an Earth-sized planet around Proxima Centauri is at the absolute edge of what's possible. The contrast ratio, the difference in brightness between the star and the planet, is enormous. Proxima b reflects only a tiny fraction of the light it receives from its star, making it roughly 10 million times fainter than Proxima itself. Detecting that faint signal requires extraordinary instruments, advanced coronagraphs, and clever data processing techniques. Several next-generation telescope concepts are specifically designed to tackle this challenge. The Habitable Worlds Observatory, a proposed NASA mission that would launch sometime in the 2030s or 2040s, aims to directly image and characterize dozens of potentially habitable exoplanets. Alpha Centauri's system would be among its primary targets. Similarly, the European Southern Observatory is developing concepts for extremely large ground-based telescopes with adaptive optic systems capable of correcting for atmospheric turbulence with unprecedented precision. These instruments won't just take pictures, they'll split the planet's light into spectra, revealing the chemical fingerprints of molecules in its atmosphere. Oxygen, ozone, methane, water vapor, carbon dioxide, each has a unique spectral signature. By analyzing these signatures, astronomers can infer not just what gases are present, but in what quantities and possibly even whether they're in chemical equilibrium or being replenished by biological processes. This is where the search for life becomes real. On Earth, the presence of large amounts of oxygen in our atmosphere is a biosignature, a sign of life. Oxygen is highly reactive and would quickly combine with other elements if it wasn't constantly being replenished by photosynthesis from plants, algae, and cyanobacteria. If we detected significant oxygen along with methane and water vapor in the atmosphere of Proxima b, it would be a compelling, though not definitive, sign of biological activity. But we have to be careful. False positives are possible. Oxygen can be produced by non-biological processes, such as the photodissociation of water molecules by ultraviolet light, followed by the loss of hydrogen to space. This is thought to have happened on Venus early in its history. Methane can be produced geologically through reactions between water and certain types of rocks at high temperatures. The real power comes from looking at combinations of gases, examining ratios and patterns that would be difficult to explain without invoking biology. Let me share something that might blow your mind. Right now, at this very moment, if there's an advanced civilization on Proxima b with technology similar to ours, they could be observing Earth. From their perspective, our Sun would appear as a relatively bright star, and with powerful enough telescopes, they could detect Earth as a pale blue dot next to it. They could analyze our atmosphere and see oxygen, methane, water vapor, and even artificial pollutants like chlorofluorocarbons that don't exist naturally. They would know we're here. They would know we're technologically advanced. And if they've been watching for a while, they would have seen our atmosphere change dramatically over the past couple of centuries as industrialization filled it with carbon dioxide and other anthropogenic gases. In a very real sense, we've been broadcasting our presence to the universe not through intentional radio signals, but through the chemical alteration of our planet's atmosphere. This raises profound questions. If we can detect biosignatures on exoplanets and If those planets harbor intelligent life, are we prepared for what comes next? The implications span everything from philosophy and theology to international policy and planetary security. These aren't abstract concerns anymore. With systems like Alpha Centauri so close and with our technology advancing so rapidly, we might face these questions within our lifetimes. But let's bring this back to the science. The Alpha Centauri system offers another advantage that makes it uniquely valuable for study. Proximity enables mission concepts that would be impossible for more distant stars. Several groups have proposed sending miniature spacecraft to Alpha Centauri using breakthrough technologies. The most well-known is Breakthrough Starshot, an initiative announced in 2016 that envisions launching thousands of tiny spacecraft, each weighing just a few grams, accelerated to 20% the speed of light using powerful ground-based lasers. At that velocity, these nano spacecraft could reach Alpha Centauri in about 20 years, fly through the system capturing images and data, and transmit their findings back to Earth. The technical challenges are immense. Accelerating something to 20% light speed requires lasers with combined power in the hundreds of gigawatts, focused with extraordinary precision. The spacecraft would need to be robust enough to survive impacts with interstellar dust particles that, at that velocity, would hit with the force of explosions. The communication systems would need to transmit signals across 4 light-years with just milliwatts of power. And all of this would need to fit on a wafer-scale device smaller than a smartphone. Yet none of these challenges are fundamentally impossible. They're engineering problems, difficult but potentially solvable with sufficient resources and technological development. If such a mission succeeded, if we actually sent probes to Alpha Centauri and received close-up images and data from planets there, it would be one of the greatest achievements in human history. We would have reached another star system, we would have extended our presence beyond the Sun's gravitational domain and touched another world. Imagine receiving those first images. The transmission would take 4.2 years to reach Earth, traveling at the speed of light. Mission control would wait anxiously as the signal, incredibly faint after crossing interstellar space, was picked up by massive radio dishes. The data would be processed, decoded, and slowly, pixel by pixel, the first close-up image of an exoplanet would appear on screens around the world. What would we see? Mountains and valleys, oceans and clouds, a barren, radiation-scorched landscape? Or perhaps, just perhaps, signs of something more. Structures that don't look natural, patterns in the landscape suggesting organization, lights on the night side. The possibilities are both terrifying and exhilarating. Even if we don't find life, the scientific return would be immeasurable. We'd learn about geology on other worlds, atmospheric dynamics under different conditions, the long-term evolution of planets subjected to stellar flares, and countless other phenomena that we can only speculate about from a distance. Each discovery would refine our understanding of how planets work, how they form, and what makes them habitable. And here's something that often gets overlooked in discussions of exoplanets. Studying other worlds helps us understand our own. Earth isn't a cosmic accident. The conditions that allow life here are the result of billions of years of planetary evolution, influenced by factors like our distance from the Sun, the presence of the Moon to stabilize our axial tilt, Jupiter's gravity shielding us from excessive comet impacts, and the particular chemistry of our atmosphere and oceans. By studying planets in the Alpha Centauri system, we create a comparison set. We can ask, what's universal and what's unique? Do all rocky planets in habitable zones develop plate tectonics, or is Earth special? Do magnetic fields strong enough to protect atmospheres develop naturally, or did Earth get lucky? How common are moons like ours that stabilize climates over geological timescales? These questions go to the heart of understanding our place in the cosmos. There's also a darker side to this exploration that we need to confront. The term terrifying truth in our discussion isn't just about radiation or inhospitable conditions. It's about confronting the possibility that we might be alone, or conversely, that we might not be. Both possibilities are unsettling in different ways. If we thoroughly explore the Alpha Centauri system and find no signs of life, not on Proxima b, not on any moons around a potential gas giant near Alpha Centauri A, not anywhere, what does that tell us? Given how close these stars are and how thoroughly we could potentially study them with future technology, finding nothing would be significant. It wouldn't prove we're alone in the universe, but it would suggest that life might be rarer than we hope. The Fermi paradox haunts these discussions. If life is common, if intelligence arises frequently, where is everyone? Our galaxy is nearly 14 billion years old. Stars like Alpha Centauri A are only slightly younger than the universe itself. If life arose there, it had billions of years to evolve, to develop technology, to spread. The fact that we don't see obvious signs of advanced civilizations, megastructures harvesting stellar energy, or artifacts in our solar system suggests either that such civilizations are rare, that they don't last long, or that they choose not to make themselves obvious. Each option has troubling implications. If technological civilizations are rare, we might face challenges ahead that are nearly impossible to overcome. If they don't last long, we might be approaching our own filter, some universal barrier that emerging civilizations rarely survive. If they exist but remain hidden, we have to ask why and whether making ourselves known is wise. On the other hand, if we find evidence of life, even microbial life, in the Alpha Centauri system, the implications are equally profound. It would suggest that life arises readily when conditions permit. It would imply that the galaxy could be teeming with living worlds. And it would raise the probability that somewhere out there, on planets we haven't even discovered yet, intelligence has emerged. Finding life on Proxima b would be especially significant because of the challenging conditions there. If life can thrive on a world bombarded by stellar flares, bathed in radiation, potentially tidally locked with extreme temperature gradients, then life might be possible in environments we've dismissed as too harsh. It would expand the habitable zone concept dramatically, not just in terms of distance from a star, but in terms of the range of stellar types and radiation environments where life can exist. This connects to a broader shift happening in astrobiology. We're moving away from the idea that Earth is the template and recognizing that life elsewhere might be radically different. It might use different chemistry, thrive at different temperatures, require different energy sources. The building blocks, the fundamental requirements, might be universal: liquid solvents, organic chemistry, energy flow, but the specific implementations could vary enormously. Consider the subsurface oceans that might exist on moons around a gas giant in the Alpha Centauri system. These oceans would be completely dark, never seeing starlight. Any life there would need to derive energy from chemical reactions, perhaps at hydrothermal vents, similar to those on Earth's ocean floors. Such life wouldn't photosynthesize, it wouldn't know what light is, at least not visible light. Its entire evolutionary history would unfold in eternal darkness, yet it could be complex, diverse, and thriving. Now let's talk about something that makes Alpha Centauri even more intriguing from a long-term perspective: its motion through space. Stars don't remain at fixed distances from each other. They orbit through the galaxy, and over millions of years, their positions change dramatically. Alpha Centauri is currently approaching us. In about 28,000 years, it will reach its closest approach at a distance of roughly 3.1 light-years. After that, it will begin moving away, eventually receding far beyond its current distance. This movement has implications for any future interstellar mission. The closer the target, the easier it is to reach with available technology. If humanity develops the capability for interstellar travel in the next few centuries, Alpha Centauri will be an even more accessible target than it is now, but if we wait too long, if we don't develop that capability until tens of thousands of years from now, we'll have missed our window of maximum proximity. There's a bittersweet quality to this cosmic timing. We exist at a moment when our nearest stellar neighbors are relatively close, when the challenges of reaching them, while still immense, are perhaps surmountable with conceivable technology. We're also at a moment when our telescopes are becoming powerful enough to study these systems in meaningful detail. This convergence of proximity and technological capability feels almost fortuitous, though of course it's not. Many generations of humans have looked at Alpha Centauri without the tools to understand it. We happen to be among the first who can. Let me take you back to Proxima Centauri for a moment and share some recent findings that are genuinely disturbing. In late 2025, a team using the Atacama Large Millimeter Array, or ALMA, conducted observations of Proxima at millimeter wavelengths, searching for cold dust and debris in the outer regions of the system. They found something unexpected, asymmetries in the dust distribution that suggest the presence of an additional massive planet, or possibly even a brown dwarf in a distant orbit. This potential outer companion, if it exists, would orbit far beyond Proxima d, possibly at distances of dozens of astronomical units. Its gravitational influence could explain some of the orbital peculiarities observed in the inner planet's dynamics. But here's the unsettling part. If there's a massive, unseen companion in the Proxima system, its gravitational perturbations could periodically destabilize orbits of comets and asteroids in the system's outer reaches, sending them careening into the inner system. This would create periodic impact events on planets like Proxima b, similar to the late heavy bombardment that Earth experienced roughly 4 billion years ago. Such events would be catastrophic for any surface life, potentially sterilizing the planet repeatedly over geological timescales. Yet paradoxically, these impacts also deliver water and organic compounds, potentially seeding planets with the ingredients for life. It's a cycle of destruction and renewal playing out over billions of years. The possibility that we're looking at a planetary system in a state of ongoing bombardment, where any life that arises must constantly adapt to survive periodic extinction events, is both frightening and fascinating. It would make Proxima b a proving ground for evolution under extreme stress, potentially producing organisms with incredible resilience and adaptability. There's another aspect of the Alpha Centauri system that deserves attention: the metallicity of the stars, which refers to the abundance of elements heavier than hydrogen and helium. Spectroscopic observations have revealed that Alpha Centauri A and B have metallicities similar to or slightly higher than our Sun. This is significant because metallicity strongly correlates with the presence of planets, especially rocky planets. Stars form from collapsing clouds of gas and dust. The metals, in astronomical terms, everything heavier than helium, provide the raw materials for planet formation. Higher metallicity means more rocky material available to aggregate into planets. The fact that Alpha Centauri A and B are metal-rich suggests they should have robust planetary systems, which makes the current scarcity of confirmed detections all the more puzzling and frustrating. Where are the planets? We know they should be there. The physics says they should have formed. Yet our observations have been surprisingly sparse in confirmed detections around Alpha Centauri A and B. Part of this is observational bias. The binary nature makes observations challenging. The stars are bright, which creates contrast problems for direct imaging. Their positions on the sky change due to their mutual orbit, complicating long-term radial velocity measurements. But as technology improves, as we deploy more sensitive instruments and longer observation baselines, the planets are starting to reveal themselves. The tentative detection at Alpha Centauri A is just the beginning. Over the next few years, we should expect more announcements, more candidates, and eventually confirmed planets that we can study in detail. Each discovery will be a piece of the puzzle, helping us understand how this complex triple star system gave birth to worlds and whether any of those worlds harbor life. Proxima Centauri's metallicity is slightly lower than the Sun's, which initially puzzled astronomers. How did such a small, metal-poor star manage to form multiple planets, including rocky worlds? The answer might lie in the efficiency of planet formation around low-mass stars. Because the protoplanetary disk around a small star has less mass to begin with, even a lower metallicity can produce planets if the formation process is efficient enough. Recent computer simulations of planet formation around M-dwarfs like Proxima suggest that these stars might actually be quite efficient at producing rocky planets in close orbits. The smaller mass of the star means the protoplanetary disk is more compact, concentrating material in the region where terrestrial planets form. This could explain why red dwarfs, despite being the smallest and coolest stars, might be among the best places to look for Earth-sized worlds. This brings us to a statistical reality that's both encouraging and overwhelming. Red dwarfs make up roughly 75% of all stars in our galaxy. If most of them have planets, and if a significant fraction of those planets are in habitable zones, then the Milky Way could host tens of billions of potentially habitable worlds. Proxima b wouldn't be special in terms of its existence, but it would be special because of its proximity, making it one of the few such worlds we could realistically study in detail or even visit. Yet there's a counter-argument to this optimism. Just because a planet is in the habitable zone doesn't mean it's habitable. Proxima b demonstrates this perfectly. It's at the right distance for liquid water, but the stellar activity, tidal locking, and radiation environment create enormous challenges for habitability. Many of those tens of billions of planets around red dwarfs might face similar issues. The question isn't just how many planets exist, but how many provide stable, benign environments over the billions of years required for complex life to evolve. This is where Alpha Centauri A becomes fascinating in a different way. As a G-type star, it's similar to our Sun. It's stable, long-lived, and relatively quiet. A planet in its habitable zone wouldn't face the extreme stellar activity that plagues Proxima b. It would receive steady, consistent radiation across a spectrum similar to what Earth receives. If such a planet exists, and if it has the right mass, atmosphere, and magnetic field, it could be genuinely Earth-like in ways that Proxima b probably isn't. The potential gas giant at 2 astronomical units doesn't rule out inner rocky planets. In our own solar system, we have both. Jupiter sits in the outer system while Earth, Venus, Mars, and Mercury orbit closer to the Sun. A similar architecture around Alpha Centauri A would be entirely plausible. There could be rocky worlds at distances of 0.5 to 1.5 astronomical units orbiting in the star's habitable zone, protected by the giant planet's gravitational influence from excessive comet impacts. These hypothetical inner planets around Alpha Centauri A are the holy grail of exoplanet research. If they exist, if we can detect them, and if we can characterize their atmospheres, they would become prime targets in the search for life beyond Earth. Unlike Proxima b with all its complications, a true Earth analog around Alpha Centauri A would be a world where we could reasonably expect Earth-like conditions to develop and persist over billions of years. The search for these planets is ongoing. Multiple research teams are planning observations with upcoming instruments specifically designed to detect and characterize small planets around nearby stars. The upcoming Extremely Large Telescope in Chile, with its 39-meter primary mirror, will have the light-gathering power and angular resolution to potentially image planets directly. The Nancy Grace Roman Space Telescope, launching later this decade, will conduct microlensing surveys and direct imaging campaigns that could reveal planets we've missed with other methods, and there are more exotic proposals on the drawing board. Solar gravitational lens missions would use the Sun's gravity as a natural telescope, positioning a spacecraft at distances beyond 600 astronomical units, where the Sun's gravity focuses light from distant objects. From that vantage point, we could potentially obtain images of exoplanets with resolution measured in kilometers, enough to see continents, oceans, and possibly even signs of civilization. Alpha Centauri would be an ideal target for such a mission. The distance is still enormous, requiring decades of travel time even with advanced propulsion, but the scientific return would be revolutionary. We would go from seeing exoplanets as points of light or, at best, fuzzy blobs, to actually mapping their surfaces, observing weather patterns, seasonal changes, and geological features. Let me bring this back to something more immediate and tangible. Right now, in observatories around the world, astronomers are collecting data on the Alpha Centauri system. Every photon captured, every spectrum recorded, every tiny wobble measured adds to our understanding. This isn't some distant future scenario. This is happening now. The data that will reveal the nature of these worlds is being collected in real time. There's something profound about the collaborative nature of this enterprise. Teams in Chile use ALMA to study dust and debris. Teams in Hawaii use ground-based telescopes with adaptive optics. The James Webb Space Telescope, operated by NASA, ESA, and CSA, points its instruments at Alpha Centauri from its position in space. The ESO's Very Large Telescope in Chile conducts radial velocity measurements. All of this data gets shared, analyzed, cross-referenced, and synthesized into a growing understanding of our nearest stellar neighbors. The international cooperation in astronomy stands in stark contrast to many other human endeavors. Scientists from dozens of countries work together, share data freely, and build on each other's discoveries regardless of political boundaries or national interests. In this pursuit of knowledge about Alpha Centauri, we see humanity at its best, united by curiosity and the desire to understand our place in the universe. But there's also competition, healthy scientific competition that drives progress. When a team announces a tentative detection like the candidate planet around Alpha Centauri A, other teams rush to confirm or refute it. This is how science self-corrects. No single observation, no matter how careful, is accepted at face value. Everything must be verified independently, challenged, tested against alternative explanations. This is why the current status of the Alpha Centauri A candidate remains tentative. Until other teams observe the same signal, until we rule out instrumental artifacts and other explanations, we maintain scientific skepticism. It's frustrating for the public and even for scientists who want answers now, but it's necessary. The history of exoplanet research is littered with detections that didn't hold up under scrutiny, signals that turned out to be stellar activity, instrumental noise, or data processing errors. Yet when a planet detection is confirmed, when multiple independent teams using different methods all agree that yes, there's a planet there, the feeling is electric. I've spoken with astronomers who describe the moment of confirmation as one of the highlights of their careers. You're the first human being to know with certainty that a new world exists. You've added a planet to humanity's cosmic census. That's a profound privilege. Let's talk about what might happen if and when we confirm an Earth-like planet around Alpha Centauri A. The announcement would likely come through a press release from the observatory or space agency involved, followed by publication in a peer-reviewed journal. The media would cover it extensively. Social media would explode with excitement and speculation, and then the real work would begin. The planet would immediately become the most important target for every major astronomical facility. Observing time, which is fiercely competitive and allocated years in advance, would be reallocated to study this world. We'd want to measure its mass precisely using radial velocity. We'd want to determine its radius through transit observations if we're lucky enough that the planet passes in front of its star from our perspective. We'd want to characterize its atmosphere through transmission spectroscopy, studying how starlight filters through the planet's atmosphere during transits. If we could determine both mass and radius, we could calculate the planet's density, which tells us about its composition. A density similar to Earth's would indicate a rocky world with an iron core. Lower density might suggest a water world or a planet with a thick hydrogen atmosphere. Higher density could mean an iron-rich composition, perhaps the remnant core of a former gas giant that lost its outer layers. Atmospheric characterization would be the next frontier. This is where biosignatures come into play. We'd look for oxygen, ozone, methane, water vapor, and carbon dioxide. We'd measure their abundances and look for combinations that suggest biological processes. We'd also look for signs of geological activity, volcanic gases that indicate a dynamic interior, which is important for maintaining a habitable surface through plate tectonics and magnetic field generation. The timescale for all of this is uncertain. With current technology, characterizing the atmosphere of an Earth-sized planet around a Sun-like star is at the very edge of what's possible, and only for the nearest systems. Alpha Centauri's proximity helps enormously, but we're still talking about incredibly challenging observations requiring hundreds of hours of telescope time and sophisticated data analysis. Next-generation instruments will make this easier. The Habitable Worlds Observatory, if funded and built as planned, would be specifically designed for this task. It would have coronagraphs capable of blocking the light from sun-like stars well enough to image rocky planets directly. It would have spectrographs sensitive enough to characterize their atmospheres in detail, and Alpha Centauri would be among its first targets. But that mission is still years, possibly decades away. In the meantime, we work with what we have. We push current instruments to their limits. We develop new data analysis techniques. We build better models of planetary atmospheres to help interpret observations. And we wait, sometimes patiently, sometimes not, for technology to catch up with our ambitions. There's something deeply human about this impatience. We want answers now. We want to know if we're alone, if there are other worlds like ours, if life has emerged elsewhere in the universe. These questions have haunted humanity for millennia, appearing in our myths, our religions, our philosophy. Only now, for the first time in human history, do we have the tools to actually answer them. Alpha Centauri represents our best hope for answers in the near term. It's close enough to study in detail. It has the right types of stars. It appears to have planets. Everything we need is there. We just need to look carefully enough with sensitive enough instruments to reveal what's been hiding in plain sight for billions of years. Let me share something that often gets lost in technical discussions of exoplanets: the sheer improbability that we exist to have this conversation. Earth formed 4.5 billion years ago from a disk of dust and gas around the young sun. For hundreds of millions of years, it was a hellscape of volcanic activity and asteroid impacts. Gradually, conditions stabilized. Water accumulated, possibly delivered by comets. The first self-replicating molecules emerged through processes we still don't fully understand. Life began. For billions of years, that life remained simple, single-celled organisms in the oceans. Then, roughly 600 million years ago, complex multicellular life exploded in diversity. Animals evolved, colonized the land, diversified into millions of species. One lineage developed larger brains, tool use, language, and eventually civilization. That's us, products of 4.5 billion years of planetary evolution and biological diversification. Now we're turning our attention to other star systems, asking whether similar processes have unfolded there. The fact that we can ask this question, that we've developed the technology to potentially answer it, is itself extraordinary. We're made of atoms forged in stars, pondering whether there are other arrangements of atoms around other stars that have also developed the capacity for self-reflection and curiosity. If there's life on Proxima b or on a planet around Alpha Centauri A, it went through its own evolutionary journey. It faced its own challenges, adapted to its own environment, and developed its own solutions to the problems of survival and reproduction. That life might be nothing like Earth life. It might use different biochemistry, different energy sources, different strategies for information storage and inheritance, or it might be surprisingly similar. There are reasons to think that certain solutions to biological problems are universal. DNA-like molecules for information storage, proteins for catalysis and structure, lipid membranes for compartmentalization, these might emerge independently on any world where life arises because they're simply the best solutions to fundamental challenges. This concept of convergent evolution, where unrelated organisms evolve similar features because they face similar challenges, might extend to a cosmic scale. Eyes have evolved independently dozens of times on Earth because light is such a valuable source of information about the environment. If there's complex life on another world with a transparent atmosphere and a bright star, chances are good that life would evolve light-sensing organs too. But there would also be profound differences shaped by local conditions. Life on Proxima b, if it exists, might have evolved extraordinary resistance to radiation, cellular repair mechanisms far more efficient than anything on Earth. It might have adapted to the red light of its star using pigments that capture those wavelengths efficiently. If the planet is tidally locked, life might be concentrated in the twilight zone between the day and night sides, taking advantage of moderate temperatures while avoiding the extremes. Imagine ecosystems adapted to live under constant stellar flares, organisms that can detect the magnetic field disturbances that precede a flare and quickly seek shelter, perhaps underground or underwater. Think about chemosynthetic organisms thriving in subsurface oceans, completely independent of surface conditions, building complex ecosystems in eternal darkness. These aren't just science fiction scenarios, they're possibilities we have to seriously consider when thinking about life in extreme environments. The study of extremophiles on Earth has revolutionized our understanding of life's limits. We've found organisms thriving in boiling water, in acid strong enough to dissolve metal, in the frozen soil of Antarctica, kilometers beneath the ocean in conditions of crushing pressure and total darkness. Even inside nuclear reactor cores bathed in lethal radiation. Life on Earth has proven far more resilient and adaptable than we once imagined. If Earth life can survive in such extreme conditions, why not on Proxima b? Why not in the subsurface oceans of moons around Alpha Centauri A? The habitable zone concept, useful as it is, might be too conservative. It defines where liquid water can exist on a surface, but it doesn't account for subsurface habitability, tidal heating, or exotic chemistries that might support life without liquid water at all. This is why actually visiting these worlds becomes so important. Remote observation can only tell us so much. We can detect atmospheric biosignatures, but we can't definitively prove their biological in origin without ruling out all possible abiotic explanations. We can measure surface temperatures and compositions, but we can't explore subsurface oceans or caves where life might be hiding. Eventually, to really answer the question of whether life exists on these worlds, we'll need to send probes, landers, and potentially even human explorers. The technological challenges of interstellar travel are immense, but they're not insurmountable. We already have propulsion concepts that could, in theory, reach Alpha Centauri within a human lifetime. Nuclear pulse propulsion, where spacecraft are propelled by detonating nuclear bombs behind them, could achieve several % of light speed. Antimatter rockets, if we could produce and store antimatter in sufficient quantities, could reach even higher velocities. And laser sail concepts like breakthrough Starshot could potentially hit 20% light speed, reaching Alpha Centauri in roughly 20 years. Each approach has severe technical challenges. Nuclear pulse propulsion requires overcoming political and environmental concerns about launching nuclear material into space. Antimatter production is incredibly expensive and inefficient with current technology. Laser sails require enormous ground-based infrastructure and face challenges with deceleration at the target system. But none of these challenges are physical impossibilities. They're engineering problems that could be solved with sufficient time, resources, and motivation. What would motivate humanity to undertake such an expensive, long-term project? The detection of biosignatures on a planet around Alpha Centauri might do it. If we found compelling evidence of life, perhaps even technological life, the drive to make contact, or at least to study it up close, would be powerful. It would become one of the defining goals of human civilization, something worth dedicating enormous resources toward. But there's also a darker motivation: survival. If we detect signs that our own planet is becoming uninhabitable, either through environmental catastrophe, resource depletion, or some other existential threat, the knowledge that there are potentially habitable worlds within reach could spur desperate efforts to reach them. The Alpha Centauri system could become humanity's backup plan, our insurance policy against existential risk. This is where the discussion becomes uncomfortable. Interstellar colonization raises profound ethical questions. If there's life on Proxima b or elsewhere in the system, do we have the right to interfere with it? Do we risk contaminating those ecosystems with Earth organisms? Even if the worlds are lifeless, do we have the right to claim them, to terraform them, to remake them in Earth's image? These aren't hypothetical questions. The decisions we make now about planetary protection, about how we conduct space exploration, about what protocols we establish for contact with potential alien life, will shape humanity's future relationship with the cosmos. We need to get this right, to think carefully about our responsibilities as we venture beyond Earth. There's also the question of what we might find. The term terrifying truth keeps coming back because some discoveries would fundamentally challenge our understanding of reality and our place in it. Imagine if we found ruins on a planet around Alpha Centauri, evidence of a technological civilization that rose and fell long before humans existed. What would that tell us about the longevity of civilizations? What lessons would we draw about our own future? Or imagine finding a thriving technological civilization, one that's been aware of Earth and watching us for centuries or longer. How would that change human society? Would it unite us or divide us? Would we see them as potential partners, competitors, or threats? The social and psychological implications of contact with alien intelligence are impossible to fully predict. But they would undoubtedly be profound and possibly destabilizing. Even finding simple microbial life would be transformative. It would answer one of humanity's oldest questions: are we alone? The answer would be no, and that single fact would reshape philosophy, religion, science, and culture. We would know that life is not unique to Earth, that the universe is capable of generating biological complexity, that the emergence of life might be common given the right conditions. But finding nothing would be significant too. If we thoroughly explored the Alpha Centauri system with advanced probes, if we studied every planet, every moon, every possible niche where life might exist, and found no trace of it anywhere, that would be a data point as important as finding life. It would suggest that either life is rare, or that the conditions required for it are more specific and fragile than we thought. The Fermi paradox would loom even larger. If our nearest neighbors, stars only 4 light-years away, show no signs of life despite billions of years of opportunity, where is everyone? The galaxy suddenly feels more lonely, more silent. We would have to confront the possibility that intelligent life might be so rare that we could be the only technological civilization in our entire galaxy, perhaps even in our local galactic cluster. That possibility carries weight. It would mean that the future of intelligence in our cosmic neighborhood depends entirely on us. If we fail, if humanity destroys itself or stagnates without spreading beyond Earth, we might be extinguishing the only light of consciousness in this region of space for millions or billions of years to come. The responsibility would be staggering. Conversely, it would mean that everything we might discover out there, every world, every resource, every beautiful vista of alien landscapes, is ours to explore and potentially to settle. The Alpha Centauri system could become humanity's first interstellar colony, the first step in a grand expansion that could eventually see our descendants spread throughout the galaxy. This brings us full circle to where we began. Alpha Centauri as a mirror. In studying these stars and their planets, we're really studying ourselves. We're asking what it means to be alive, to be conscious, to be technological. We're exploring the conditions that gave rise to us and asking whether those conditions exist elsewhere. We're confronting our fears, our hopes, our place in a vast and ancient universe that existed long before us and will continue long after we're gone. The terrifying truth about Alpha Centauri might ultimately be this: it forces us to think on cosmic timescales and face cosmic realities. Our individual lives, even our entire civilization so far, are fleeting moments in the vast sweep of astronomical time. These stars have been burning for billions of years. Their planets, if they exist, have been orbiting for equally immense periods. Whatever we discover, there has been waiting, unchanged by our ignorance of it, patient in a way that only cosmic phenomena can be patient. We're newcomers to this universe, recently evolved primates who only developed the ability to study distant stars within the last few centuries. We're looking across 4 light-years at worlds that were already ancient when our species came into existence. There's a humility in that recognition, an acknowledgement of our cosmic youth and inexperience. Yet we're also the universe's way of knowing itself, at least in this part of the galaxy. Through our telescopes and probes, through our equations and observations, the universe becomes aware of its own structure and history. When we look at Alpha Centauri, the atoms in our bodies, themselves forged in ancient stars, are observing other stars, completing a cycle of cosmic self-awareness that spans billions of years. The next few decades will be crucial. Our technology is advancing rapidly. The instruments coming online in the late 2020s and 2030s will have capabilities that would have seemed like science fiction just a generation ago. We will find planets around Alpha Centauri, A and B. We will characterize them. We will search for signs of life. And we will begin to answer questions that humans have asked since we first looked up at the night sky. Those stars that ancient humans saw, that they incorporated into their myths and navigation systems, are finally giving up their secrets. The dim red star that telescopes revealed in 1915, Proxima Centauri, turns out to host multiple planets, including one in its habitable zone. The bright binary that has guided sailors and marked the southern skies for millennia turns out to be a complex system potentially rich in worlds we haven't yet discovered. We stand at a threshold. Behind us lies all of human history, our entire story as a species confined to one planet orbiting one star. Ahead lies a future where we might become an interstellar species, where planets around Alpha Centauri and other nearby stars become as familiar to our descendants as the continents of Earth are to us. The transition from planetary to interstellar civilization is one of the great filters in the Fermi paradox, one of the challenges that might explain why we don't see evidence of advanced civilizations throughout the galaxy. Whether we successfully make that transition, whether we develop the technology and maintain the societal stability and long-term vision necessary to reach the stars, remains to be seen. But Alpha Centauri beckons. It's close enough to reach, interesting enough to study, and potentially habitable enough to settle. It represents both our nearest cosmic neighbor and our best hope for expanding beyond our home world. The terrifying truth is that we live in a universe of almost inconceivable scale and age, where we might be alone, or where we might be one of countless civilizations, and we don't yet know which. The terrifying truth is that the worlds orbiting our nearest stars might be dead, sterile rocks, or they might harbor life utterly alien to our experience. The terrifying truth is that our future, the survival and flourishing of human civilization, might depend on our ability to reach those worlds, but there's also wonder in that truth. There's excitement in standing at the beginning of an age of discovery that will make the European age of exploration look trivial by comparison. There's hope in knowing that if we can solve the technical challenges, if we can work together as a species, if we can maintain our curiosity and drive, the stars are within our reach. Alpha Centauri isn't just a point of light in the night sky anymore. It's a destination, a goal, perhaps a future home. It's where humanity's interstellar story will likely begin, where we'll take our first real steps into the galaxy. And whatever we find there, life or emptiness, habitable worlds or hostile environments, answers or new mysteries, it will change us forever. The cosmos is vast and ancient, indifferent to our existence, but we're not indifferent to it. We look outward with wonder and determination. We build telescopes and spacecraft. We ask questions and seek answers. And 4 light-years away, orbiting stars remarkably similar to our own sun, worlds are waiting to be discovered, studied, and perhaps one day visited. That's the terrifying, wonderful, humbling, exhilarating truth about Alpha Centauri, and we're only just beginning to understand it. If you made this far, please make sure to give this video a thumbs up and subscribe. And if you found this exploration of our nearest stellar neighbors fascinating and want to understand more about humanity's future in space, I invite you to watch my video called "This is Why the Moon Will Never Be a Human Home," where we explore another uncomfortable truth about our cosmic ambitions and the real challenges of becoming a spacefaring civilization. See you there.